Homework 4.4, Exponential and Logarithmic Equations, Video 6. Homework due Friday, May 29th at 11:59 p.m. This video and the preceding video are associated with homework questions 11 through 15 from Homework 4.4. In the previous video, we listed a technique for solving logarithmic equations that had logs on one side. Well, I say logs, but it only had one log. And our strategy was an unknown first step because we didn't need it, rewrite an exponential form which freed the variable from inside the logarithm. Then we finished solving, but we also have to check and discard any solution that makes any argument non-positive. So what's up with the missing first step, and why did I say logs and not log? Because of problems like this. I've kind of already given it away, but what's the main difference between this equation and the one we saw previously? The one we saw previously, log base 2 of x plus 11 equals 4, had a single log on the left side. But as the name of the video implies, there could be more than one log on that side. So why does that matter? Well, if we tried to go right into step 2, we would need to rewrite this in exponential form. But you could ask the question, what's the answer to a log do? The answer to a log is a power that turns the base into the argument, but I have two arguments because I have two logs. So I can't do step 2 if there's more than one log. So guess what we need to do first? In a single word, condense. In more than one word, if necessary, comma, condense into one log. Condense into one log. In the previous series of videos, I actually explicitly said we will be using condensing when solving logarithmic equations. Here we go. So, move number 1, condense, which means we need to revisit the product rule, the quotient rule, and the power rule. Which one will we need to condense the left side of this? Hint, there's a plus. Answer, product rule. The product rule says the sum of two logs equals the log of the product of the arguments. Now, it could have said minus, and there could have been coefficients that would have invoked the power rule. So any of the condensing scenarios we saw in the previous series of videos could pop up here. But this one's pretty easy. If we want to condense the left, condense does not have an S after the N. Well, not after the first N. If we want to condense, we just use the product rule, and the product rule says the sum of two logs can be condensed into a single log with the same base of the product of the arguments. The first argument is x, the second argument is 11x minus 1, and we have all this equal to 1. So, by condensing it into a single log, we have now put it in a position where we can rewrite it in exponential form. So let's rewrite it. And remember, the rewrite is based 100% on what the answer to a logarithm does. The answer to a logarithm is a power that turns the base into the argument. So this number is the power that turns the base into the argument. And I'm going to stop writing the fancy ones. I just write them so they don't look like L's, but I think we can pick up on context whether it's an L or a 1. I'm sorry, these fancy ones are just driving me nuts. I don't know why I suddenly decided to start writing them again. But if we rewrite the logarithm in exponential form, we get 12 to the first power equals x times 11x minus 1. At which point now we have to solve. But as I mentioned in the last video, how you solve this depends upon the caliber of equation that you have. How do we solve this guy? At the very least, we should do 12 to the first power. That's just 12. But what do your instincts say about the right side? Distribute. And we get 11x squared minus x. This looks fun. Hope I wrote this down right. I took this out of the homework. And if I miswrote it, it could be a big train wreck. X, 11x minus 1 and 1. Yep, that's correct. If you really must know, I used question 12 on the homework to build this problem. All right. Oh no, it's a quadratic equation. We have ways of making it talk. But however you choose to solve it, you're probably going to want to get it equal to 0, and since the x squared is already positive, I'm going to leave it on the right side, which means I'll empty out the left side. So if I subtract 12 from the left, I get 0, and if I subtract 12 from the right, I get x squared minus x minus 12. Now it's either a factoring or a quadratic formula issue. I get the feeling even the best of you would probably get out the quadratic formula here because the leading coefficient is 11, but I like to think I've got crazy factoring skills. Let's see if I can insta-factor. It's actually not that hard. The 11x squared had to come from 11x times x. 11 is prime. It's the 12 I've got to massage because I've got to do something that would create a negative 1 in the middle. I think 12 and 1 with a minus on the 12 and a plus on the 1 will do it. Let me mentally refoil it. There's 11x squared. There's minus 12. If I do the outside and the inside, positive 11x, negative 12x is negative 1x. I like my factorization. It's factored, it's equal to 0. I can just put each factor equal to 0 and solve. Solving x plus 1 equals 0 gives x equals negative 1. That should be kind of obvious. Solving 11x minus 12 equals to 0 is also kind of easy to do mentally, but if the size of the numbers in the problem intimidates you, work it out by hand, but you should get 12 elevenths. 12 elevenths. Now don't just say I'm done, because we have to discard any solution that makes an argument non-positive. Now that does not mean get rid of negative answers. I have seen good negative answers and bad positive answers. I've seen problems where we keep everything, and I've seen problems where we get rid of everything. And of course, I've seen problems where we keep one and get rid of the other. So unfortunately, there's no generalizations that can be made here aside from check each one in each log's argument and see if it makes it non-positive. So let's check 12 elevenths. Don't let the fraction intimidate you. That's a positive fraction. If I put it there, nothing happens to it and it stays positive. So that's okay. But what about putting 12 elevenths here? 11 times 12 elevenths minus 1 might seem intimidating until you realize that the 11s cancel. And you're left with 12 minus 1, which is positive. Positive 11, but I don't care that it's 11. I just care that it's positive. This guy does not make any non-positive arguments, so he's a keeper. What about the negative 1? Well, it didn't take long to throw it away. When I put negative 1 here, that's a problem. So the only solution to this one is 12 over 11. Real quick comment about where the negative 1 came from. Negative 1 was bad because it made both of these arguments negative. But remember when we did the product rule first, and I said that the product rule is true with a certain caveat? The caveat was all three arguments are positive. Putting a negative 1 here makes it negative, and putting a negative 1 here would also make it negative. But when I condensed it, negative times negative is positive. So technically, negative 1 would be a solution of this equation, because it would make this argument positive, because it would be negative times negative, but not that equation. So the product rule and the other rules technically only hold when all three arguments are positive. Since this negative 1 made both of these negative, but this one positive, the product rule technically does not apply when x equals negative 1. All you have to know is check for bad answers. If an answer makes a non-positive argument, throw it away. Otherwise, keep it.